the meter can is changed out and replaced by a combination meter circuit breaker, the existing feeder for the load center in the garage now requires a circuit breaker for protection. When the separate meter can without the main circuit breaker is replaced by a combination meter circuit breaker, the combination unit now assumes the role of both the meter and the main circuit breaker. However, the existing feeder to the load center in the garage still requires protection from overcurrent. The National Electrical Code, or NEC, has specific requirements for the scenario. Section 210.19 C of the NEC requires that feeders shall be protected against overcurrent in accordance with their ampacity. Section 240.21 V of the NEC specifies that for feeders having multiple branch circuits or branch circuits and outlets, each ungrounded conductor shall be protected in series by an overcurrent device rated at not more than the ampacity of the conductor. Therefore, to ensure proper overcurrent protection for the existing feeder to the load center in the garage, a circuit breaker must be installed in series with the feeder. This circuit breaker should be rated appropriately based on the ampacity of the feeder. Now let's delve deeper into the NEC requirements and other considerations for this type of electrical service upgrade. Firstly, understanding ampacity is crucial. Ampacity refers to the current carrying capacity of a conductor, typically measured in amps. It represents the maximum current a conductor can carry continuously without exceeding its temperature rating. The ampacity of a conductor is determined by factors such as its size, material insulation type, and installation conditions. NEC Table 310.15 B16 provides ampacity values for various conductors based on these factors. Secondly, overcurrent protection is essential for preventing damage to electrical equipment and reducing the risk of fire. Overcurrent can occur due to various reasons, including short circuits, ground faults, and overload conditions. Overcurrent protective devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level, thereby protecting the circuit and equipment from damage. Thirdly, the selection of the appropriate circuit breaker size is critical for ensuring both safety and proper operation of the electrical system. The circuit breaker should be rated to protect the feeder conductors against overcurrent while also allowing for normal operating current. NEC Section 240.4 provides guidance on the selection of overcurrent protective devices based on the ampacity of the conductors. Fourthly, the installation of the circuit breaker must comply with all applicable codes and standards. This includes ensuring that the circuit breaker is properly sized, installed in a suitable enclosure, and connected to the feeder conductors in accordance with manufacturer's instructions. It is also essential to verify that the circuit breaker is properly labeled to indicate its function and rating. Fifthly, grounding and bonding are critical for electrical safety. Grounding provides a path for fault current to return to the source, allowing the overcurrent protective device to trip and energize the circuit. Bonding ensures that all metal parts of the electrical system are electrically connected, minimizing the risk of electric shock. NEC Article 250 provides detailed requirements for grounding and bonding. Sixthly, coordination of overcurrent protective devices is important for ensuring selective tripping. Selective tripping means that only the overcurrent protective device closest to the fault should trip, minimizing disruption to the rest of the electrical system. This requires careful selection and coordination of circuit breakers and fuses throughout the electrical system. Seventhly, proper documentation is essential for maintaining the electrical system and ensuring compliance with codes and standards. This includes keeping records of all electrical work performed, including circuit breaker sizes, conductor ampacities, and grounding and bonding connections. It is also important to maintain up-to-date electrical drawings and diagrams. Eighthly, regular inspection and maintenance of the electrical system are necessary for ensuring its continued safety and reliability. This includes checking circuit breakers for proper operation, inspecting conductors for damage, and verifying grounding and bonding connections. Any deficiencies should be promptly corrected by a qualified electrician. Ninthly, it is essential to consult with a qualified electrician or electrical engineer for assistance with electrical service upgrades. These professionals have the knowledge and experience to ensure that the upgrade is performed safely and in compliance with all applicable codes and standards. They can also provide valuable advice on selecting the appropriate equipment and designing the electrical system. Tenthly, it is important to be aware of the specific requirements of the local electrical code. Local codes may have additional requirements that are not covered by the NEC. It is the responsibility of the electrician or installer to ensure that all work complies with both the NEC and the local electrical code. The NEC Section 110.3 He states that listed or labeled equipment shall be installed and used in accordance with any instructions included in a listing or labeling. This means that all electrical equipment must be installed and used according to the manufacturer's instructions. This is important for ensuring the safety and proper operation of the equipment. The NEC Section 110.12 addresses mechanical execution of work. Electrical equipment should be installed in a neat and workmanlike manner. This means that all wiring should be properly supported and secured, and all connections should be made tightly and securely. This is important for preventing damage to the equipment and reducing the risk of electrical shock. The NEC Section 110.14 C covers the requirements for making electrical connections. The electrical connections must be made using approved methods and materials. This includes using properly sized wire connectors and ensuring that all connections are tight and secure. This is important for preventing overheating and reducing the risk of electrical fire. The NEC Section 225.30 covers the requirements for the number of supplies to a building or structure. In general, a building or structure is only allowed to have one service. However, there are some exceptions to this rule. For example, a building or structure may have more than one service if it is large enough to require multiple services or if it is served by two or more different utilities. The NEC Section 230.70 8.1 requires that the service disconnecting means be located at a readily accessible location either outside of a building or structure or inside nearest the point of entrance of the service conductors. This allows for easy shut-off of power in case of an emergency. This disconnect is typically a main breaker. The NEC Section 250.24 covers the requirements for grounding service supplied alternating current systems. The grounded conductor must be connected to a grounding electrode system. This grounding electrode system must consist of one or more of the following: a metal underground water pipe, a metal frame of the building or structure, a concrete encased electrode, or a ground ring. This grounding system is in place to provide a low impedance path to ground in the event of a fault. In the context of upgrading a meter into a combination meter circuit breaker unit, it is crucial to consider the existing grounding and bonding infrastructure. Verify that the grounding electrode system is adequate and in compliance with current NEC requirements. Also, ensure that all metal enclosures and equipment are properly bonded together to create an effective ground fault current path. It is also important to verify the short circuit current rating, or SCCR, of all equipment. The available fault current at the service entrance must be less than or equal to the SCCR of the equipment. This is to ensure that the equipment can safely withstand the stresses of a short circuit event. The NEC Section 110.9 covers interrupting rating. Equipment intended to interrupt current at fault levels shall have an interrupting rating sufficient for the nominal circuit voltage and the current that is available at the line terminals of the equipment. Equipment intended to interrupt current at other than fault levels shall have an interrupting rating sufficient for the nominal circuit voltage and the current that must be interrupted. The NEC Section 110.10 covers circuit impedance, short circuit current ratings, and other characteristics. The overcurrent protective devices, the total impedance, component short circuit current ratings, and other characteristics of the circuit to be protected shall be selected and coordinated to permit the circuit protective devices used to clear a fault to do so such that the resultant condition of the protected equipment minimizes damage to the equipment. In summary, when upgrading a meter into a combination meter circuit breaker unit, it is essential to consider all applicable NEC requirements and best practices. This includes ensuring proper overcurrent protection, grounding and bonding, equipment ratings, and installation procedures. By following these guidelines, you can ensure a safe and reliable electrical service. The specific ampacity of the feeder conductor determines the appropriate size of the circuit breaker needed for overcurrent protection. To determine the correct circuit breaker size, consult NEC Table 310.15 B16, which provides ampacity values based on conductor size and insulation type. For example, if the feeder conductor is a 4 American wire gauge or AUG copper conductor with THHN insulation, its ampacity is typically 70 amps. In this case, a 70 amp circuit breaker would be appropriate. However, it is important to note that there are exceptions to this rule. For example, NEC Section 240.4 B allows for the use of the next highest standard overcurrent device rating if the conductor ampacity does not correspond to a standard circuit breaker size. However, this exception is subject to certain limitations. It is also important to consider the load served by the feeder when selecting the circuit breaker size. The circuit breaker should be sized to protect the feeder conductors against overcurrent while also allowing for normal operating current. This requires calculating the total load served by the feeder and selecting a circuit breaker that is appropriately sized for that load. In addition to the NEC requirements, there may be local codes or regulations that apply to electrical service upgrades. It is important to consult with the local authority having jurisdiction, or OJ, to determine if there are any additional requirements that must be met. The AHA is the entity responsible for enforcing the electrical code in a particular area. This could be a city, county, or state agency. The AHA can provide guidance on interpreting the code and ensuring that all work complies with applicable regulations. It is also important to obtain any necessary permits before starting work on an electrical service upgrade. Permits are required for most electrical work and are used to ensure that the work is performed safely and in compliance with the code. The permit process typically involves submitting an application, paying a fee, and having the work inspected by an electrical inspector. The electrical inspector will verify that the work complies with the code and that it is safe for use. In addition to the technical aspects of the upgrade, it is also important to consider the aesthetic aspects. The new meter can and circuit breaker should be installed in a location that is both functional and aesthetically pleasing. The equipment should be installed in a way that minimizes its visual impact and that blends in with the surrounding environment. It is also important to ensure that the equipment is accessible for maintenance and repairs. The meter can and circuit breaker should be installed in a location that is easy to reach and that provides adequate space for working on the equipment. In addition to the safety and code compliance considerations, it is also important to consider the cost of the upgrade. The cost of the upgrade will depend on a number of factors, including the size of the service, the type of equipment used, and the labor rates in the area. It is important to obtain multiple quotes from qualified electricians before starting work on the upgrade. This will help to ensure that you are getting a fair price for the work. It is also important to ask the electrician about their experience and qualifications. The electrician should be licensed and insured and should have experience performing similar upgrades. It is also a good idea to ask for references from past customers. By following these guidelines, you can ensure that your electrical service upgrade is performed safely in compliance with the code and at a reasonable cost. Remember to always consult with a qualified electrician or electrical engineer for assistance with electrical work. These professionals have the knowledge and experience to ensure that the work is performed safely and correctly. The combination meter circuit breaker unit should be listed by a recognized testing laboratory such as Underwriters Laboratories or all. This listing indicates that the equipment has been tested and found to meet safety standards. Look for the UL mark on the equipment to verify that it is listed. It is also important to verify that the equipment is rated for the voltage and current that it will be used in. The equipment should be rated for the voltage of the electrical service, such as 120 volts or 240 volts, and it should be rated for the maximum current that the service can provide. This information is typically found on the equipment's nameplate. The equipment should also be installed in accordance with the manufacturer's instructions. The manufacturer's instructions provide detailed information on how to install the equipment safely and correctly. It is important to read and follow these instructions carefully. If you are not comfortable performing the electrical work yourself, it is best to hire a qualified electrician. Electrical work can be dangerous, and it is important to have it done by someone who is trained and experienced. A qualified electrician will be able to ensure that the work is done safely and in compliance with the code. Furthermore, the grounding electrode conductor, often referred to as GEC, plays a pivotal role in the safety and effectiveness of the grounding system. The size of the grounding electrode conductor is determined by NEC Table 250.66, which is based on the size of the service entrance conductors. The grounding electrode conductor connects the service equipment, such as the neutral busbar and the combination meter circuit breaker unit, to the grounding electrode system. The grounding electrode system typically consists of one or more grounding electrodes, such as a ground rod, a metal water pipe, or a concrete encased electrode, often referred to as a UFO ground. The grounding electrode system provides a low impedance path to ground, which helps to minimize the voltage on metal parts of the electrical system and provides a path for fault current to return to the source. It is essential to ensure that the grounding electrode conductor is properly sized and installed in accordance with the NEC requirements. The grounding electrode conductor should be securely connected to the grounding electrode system and to the service equipment. The connection should be made using approved methods and materials, such as exothermic welding or listed connectors. In addition to the grounding electrode conductor, the equipment grounding conductors, often referred to as EGC, are also essential for safety. The equipment grounding conductors provide a path for fault current to return to the source from metal parts of the electrical system that are not normally current carrying, such as the metal enclosures of electrical equipment and the metal raceways that enclose conductors. The equipment grounding conductors are typically sized according to NEC Table 250.122, which is based on the rating of the overcurrent protective device protecting the circuit. The equipment grounding conductors should be securely connected to the metal parts of the electrical system and to the grounding busbar in the service equipment. The connections should be made using approved methods and materials, such as listed connectors or grounding screws. It is also important to ensure that the equipment grounding conductors are properly installed and protected from damage. The equipment grounding conductors should be run along with the circuit conductors and should be protected from physical damage. They should also be protected from corrosion. In addition to the grounding and bonding requirements, it is also important to consider the surge protection requirements. Surge protection devices, often referred to as SPD, are designed to protect electrical equipment from voltage surges, such as those caused by lightning strikes or utility switching. Surge protection devices should be installed at the service entrance and other strategic locations throughout the electrical system. The surge protection devices should be sized and installed in accordance with the manufacturer's instructions and the NEC requirements. It is also important to ensure that the surge protection devices are properly grounded. The grounding conductor for the surge protection device should be connected to the grounding busbar in the service equipment. The surge protection devices should be regularly inspected and tested to ensure that they are functioning properly. If a surge protection device fails, it should be replaced immediately. By following these guidelines, you can ensure that your electrical service is properly grounded, bonded, and surge protected. This will help to protect your electrical equipment from damage and to ensure the safety of yourself and others.